Let me just begin with what a sequence is. I hope some of you have studied these things already, but just to define sequence, I mean, before defining what a sequence is, let me just ask you a few questions. Those who know the answer, please respond to this. Otherwise, please be on mute. Now, see, if you give this number series, can you guess what number comes next? Right? Can anybody guess what number comes next in this sequence? Right? Somebody is saying 243 into 3. Fine. Right? See here, they're all just powers of 3. You can see 3 power 1, 3 power 2, 3 power 3, and so on. So when this is the sixth number here, you can easily expect it is 3 to the power of 6, 729. Correct? Fine, good. Look at this. Can you expect what number comes next in this sequence? Look at all those numbers carefully. Right? See, people are saying 28. Yes. I hope you understand 1 plus 2, it is 3, then 3 plus 3, 6, then 6 plus 4, the difference in any two successive numbers, actually it is increasing. Like 2, then 3, then 4, then here you see 5, then it is 6. So automatically one can expect the next number will be at a distance of 7 units. So it is 21 plus 7, it is 28. Right? So like that you can expect this number also. Good. So these are some series of numbers and from which you can expect the next number, right? Fine. Look at this sequence, this number series. And in fact, you see there is a clear relationship between this series of numbers and, this diagram here. Identify what number comes next in this, number series. You must know. Yes, somebody is saying it 144. Yes, it's exactly 144. I hope you remember this is the popular what you call Fibonacci series, right? And see what's the relation between these two. Fibonacci series is a very popular. Perhaps some of you are already aware of this. If you look at this diagram, the sunflower. As you know, sunflowers are more than just beautiful. They're also a mathematical marvel. See the pattern of seeds within a sunflower. You can look at them. The pattern of seeds here. This pattern follows what you call this Fibonacci sequence, right? The numbers, what you can observe here, these, the pattern of these seeds and this number sequence has a very close relation. And as you know, when you refer to your mathematics notebook, when you refer to your mathematics classes, in this sequence, one number can be obtained by adding the previous two numbers, right? Each number in the sequence is the sum of previous two numbers, correct? And in sunflower, you see, you can observe two spirals here, right? One is moving in clockwise direction, the other one is moving in anti-clockwise direction. So in sunflowers, the spirals you see in the center are generated from this sequence only, right? There are two series of curves winding in opposite directions. One is in clockwise and another one is in anti-clockwise directions. And both are starting at the center and stretching out to the petals, right? Both the spirals, they are starting at the center and moving towards the petals here. And here you see each seed sitting at a certain angle from the neighboring seeds to create a spiral. So that's all the seeds are not just, moving towards, they're all not at a particular, what you call 90 degrees angle. They're all having a different angle. They're all sitting a particular angle, which creates what you call a spiral there. And in fact, you see, if you look at that angle, and that angle, we call it as what you call, golden angular golden ratio, right? So when all these seeds follow this particular mathematical principle of golden ratio, then you see we got what you call this particular Fibonacci sequence. Or you see, if you just observe the numbers which are near to these pedals, those numbers are what you call any two successive numbers in this Fibonacci sequence, right? Anyway, I'm not getting into all those details. If you want to know more about this sunflower or Fibonacci sequence, you can just Google it, right? Now the question comes here, as you can expect the number sequence very easily. Can I ask you, what is the, look at the first sequence here, 3, 9, 27, and so on. Can you find out the nth term in this series? I mean, I can say it like this. In this sequence, in this series of numbers, 3 is the first number, 9 is the second number, 27 is the third number, and so on. You guessed what you call the sixth number as 729. In a similar way, can you guess what is the nth number? If I say nth number, in that, if I substitute n is equal to 1, I must get number 3, the first number. If I substitute n is equal to 3 in that, I must get the second number, 9. Like that, you see, can you expect the nth number in this sequence? See, it is 3 to the power of n. When it is 3 power n, you see, when you substitute n is equal to 1, it is 3 power 1, 3. When you take n is equal to 2, it is 3 power 2, 9, and so on. That's how you can see the nth number in this sequence is 3 to the power of n, and n takes all positive integers. Right? Understand all the numbers here. It is, in fact, I can say it is a set of numbers. Set of numbers like 3, 9, 27, and so on. That set of numbers are all following what you call a particular rule, and that rule is exactly this 3 to the power of n. Right? See here, this is a set of numbers 3, 9, 27, 81, and so on. There are infinitely many numbers in this set. Right? All these numbers are particularly following one rule, which is 3 to the power of n. And for n is equals to different values, you are getting different numbers of this set. Right? Understand, from this particular rule, we are getting all these numbers. For different values of n, we are getting different numbers of this set. And the two, you are getting them in a sequence. I mean, when you take n is equal to 1, you are getting the first number. When you take n is equal to 2, you are getting the second number. When you take n is equal to 3, we are getting the third number. And I mean, you are getting all the numbers in this set as sequentially. That's how we call this set of numbers as a sequence. In fact, you see, sequence is only a set of numbers which follow a specific rule, in which all the numbers follow a specific rule. Right? Understand, similarly in the second sequence, if you just look at all these numbers, nth number can be found as this: an is equals to n square plus n by 2. If you look at this, you see, if you take n is equals to 1, if you take n is equals to 1, you see 1 plus 1, 2 by 2, which is 1. First number is 1. If you take n is equal to 2, right, you must get the second number, right? So n square, 2, 4 plus 2, 6 by 2, it is 3. So we got the second number. If you take n is equal to 3, we must get it as the third number. Yes, 9 plus 3, 12, 12 by 2, it is 6. Like this, you see, when you substitute n is equals to 7, the seventh number, so we'll get it as 7 square, 49 plus 7, 56 by 2, which is 28. Right? Like this, we can find the nth number. And even you can observe here also, this is all a set of numbers like, 1, 3, 6, 10, 15. This is all a set of numbers. And all these numbers are following a definite rule, n square plus n by 2. That's how you see, I can here clearly identify which is the first number in the sequence, which is the second number, which is the third number. I can easily identify from this rule. Right? That's how I can call this set of numbers as a sequence. Now, similarly here also, so this is the rule we follow actually. An is equals to an minus 1 plus an minus 2. I mean, to get the next number in the sequence, we just add the previous two numbers. Isn't it? Of course, considering a naught is equals to 0, we take it like this. And you see, that is how you can look at this diagram here. This is how, we get spirals you can see in these flowers. Not only in sunflower, in many flowers like this, we get spirals of this kind. See here, we have 1, 1. Then 1, 1 is 2. Then 1 plus 2, it is 3. Then 2 plus 3, it is 5. Then 3 plus 5, it is 8. Then 5 plus 8, it is 15. I mean 13. Then when you add 13 and 8, it is 21. You see, like this, it creates spirals. Right? So that's the basic idea behind this. Now let me just define what is a sequence mathematically. Understand, to be a sequence, first of all, we should have a set of numbers. Right? When you have a set of numbers, we can take that set of numbers as a sequence if you can identify which is the first number, which is the second number, which is the third number. I mean, if all those numbers follow a specific rule, right? If that set is an ordered set, then you can call it as a sequence. In other way, mathematically speaking, see what I'm saying, you can take a set of numbers as a sequence if you can identify which is the first, which is the second, which is the nth, like this. Understand, if I say this, in this sequence, number 3 is the first one, number 9 is the second one, number 27 is the third one. What I can see, what I mean here, I can clearly define a mapping from these numbers 1, 2, 3, 4, and so on. What are all these numbers? You see, they're all set of natural numbers. From this set of natural numbers to a set of other numbers, like if I take this as capital A, if I can then create a mapping from set of natural numbers to this set of numbers, then I can take that set of numbers as a sequence, or else this mapping is from N to A as a sequence, right? Mathematically speaking, if we can define a mapping from set of natural numbers to this non-empty set capital A, then that mapping can be taken as what you call sequence. In colloquial language, if you want to remember it, understand it this way. Sequence is a set of numbers in which you can identify which is the first, second, third, and so on, right? If all these numbers are following a specific rule in which this rule follows, set of natural numbers, then we can call that set of numbers as what you call a sequence, right? Now just let me just extend this idea mathematically. Now see, when you are given a set of numbers like this, S1, S2, and so on, Sn, the same whatever I've discussed till now, corresponding to all these numbers, if you can associate them with some positive number, right? If for every positive integer n, understand, set of natural numbers are positive integers, both are same. If for every positive integer n, there is associated a unique real number Sn, then the ordered set of numbers S1, S2, and so on, Sn, is called an infinite sequence. Understand, this is an infinite sequence because it has infinite number of values in this, right? Corresponding to each number in this set, if we can map it with some positive integer, some natural number, then we can call that as a sequence. I mean, we can call then this set of numbers as a sequence, right? Then see, in this sequence, we take Sn, S suffix n, as the nth term or general term, right? You see in the previous two examples, we have written 3 to the power of n or n into n plus 1 by 2. They are all actually nth terms of the sequence, right? And symbolically, we just write, we represent a sequence like this. We'll write Sn directly in flower braces, right? We'll write Sn directly in flower braces, or sometimes we also write it as Sn, where n takes values from 1 to infinity, right? In either ways, we speak about what you call a sequence. To represent a sequence, we just write them like this, a symbolic notation. Now see, when you are given a sequence, mathematically speaking, as I told you already, when you are given a non-empty set capital A, sequence is actually a function or a mapping from set of natural numbers to the given set of numbers, right? And in particular, you see, to define a sequence, we are actually considering what you call set of numbers, right? Set of real numbers or anything you may have. In general, those set of numbers may be complex also. But in particular, if those set of numbers are only real numbers, that's how you can see here. If capital A is a subset of real numbers, this or represents real numbers, set of real numbers. And if capital A is a subset of real numbers, then we call that sequence as a real sequence. Understand? If a mapping is defined from set of natural numbers to a subset of real numbers, we call it as a simple real sequence, right? But anyway, in our discussion, we only consider real sequences. So in our further discussions, remember, if I say simply sequence, understand it is a real sequence only, right? In higher classes, if you choose mathematics as your career, you may also learn what you call complex sequences. But now, we were discussing about actually infinite sequence. But is there any possibility of getting a definite sequence? Yes, certainly it is there. See, in case if your subset of real numbers, like we are taking it as capital A, if that subset of real numbers has exactly finite number of values, then we call such a sequence as what you call a finite sequence. See, for example, if I take it like this, 2 to the power of 1, 2 to the power of 2, let us say it is 4, then 2 to the power of 8, 2 to the power of 3, then 2 to the power of 4, and so on. I'll take this up to 2 to the power of 100, let us say. See, all these are some real numbers, and all these numbers are specifically following a rule, 2 to the power of n. And moreover, there are exactly finite number of values in this sequence, in this set. There are exactly n values, 100 values only. So here, the rule what you are following is 2 to the power of n, and n takes values from n is equals to 1 to 100 only, not you are going towards infinity. Since there exist only 100 numbers which are finite, we can say this sequence as a finite sequence. You cannot take a simple finite set here, you see. If you take some simple finite set of numbers like this, I cannot take this as a sequence. There is a clear difference between finite set and finite sequence. Finite set has no rule. We can take any numbers randomly. But to be a sequence, all those numbers must follow a particular rule, right? When you have a rule specifically like this, then that finite set can be taken as a finite sequence. Okay, so that's a basic idea behind finite sequence, but there is not so much to discuss about finite sequence, but there is so much to discuss about infinite sequence. So we'll just concentrate more on what you call infinite sequence only. Infinite sequence in the sense a sequence which has infinitely many number of values in it. So this is also one example for a finite sequence here. You see 1, 3, 5, 7 up to 199. How can you write this mathematically? Can you write nth term here? Yes, you can. See, these are all actually what you call odd numbers. So to represent, as I told you already, to represent an even number, we use normally 2n, whether n is odd integer or even integer, right? Even though when it is odd integer or even integer, n, 2n becomes certainly even only. So 2n is always even, and to get odd numbers, either we can add a 1 or subtract a 1 from this, right? So in either ways we'll get odd numbers actually, but depending on the situation. So here I need to get these odd numbers when I take n starts from 1. So when I take n is equal to 1, see if I take 2n plus 1 here. For n is equals to 1, it starts from third, the second number. So since I want 1 to be the first number, I'll take this as 2n minus 1 here. So the sequence here is 2n minus 1, where n takes values from 1 to 100. Right, so when you take n is equals to 100, we'll get the last number as 199. That's how this is a finite sequence. Okay, that's a basic idea here about what a sequence and what is what you call an infinite sequence and mathematical definition for a sequence. Now see, when you define a sequence, it is actually a set of numbers, maybe some infinite number of values or finite number of values. Anyway, I'm not concentrating on finite number of values now. So you are given an infinite sequence. So there are infinitely many number of values. So even when n approaches to infinity, you will get some number in the sequence. That's the basic idea, right? So how we are defining now, for example, if we take it like this, Sn is equals to 2 to the power of n, where n approaches to n takes values from 1 to infinity. You can define it like this. So if you take n is equals to 1000, you will get some number. If you take n is equal to 1 lakh, you will get some number. When n approaches to infinity, also something you will get there, right? So what numbers you are going to get there? When you define an infinite sequence, what happens when n approaches to infinity? Whether all those numbers go towards a finite value or they go to infinity, infinity, plus infinity or minus infinity. We need to see that. And depending on that, we actually define the idea of limit. Understand what happens? Let's just look at this idea first, and then I'll explain you this geometrically. Let Sn be a sequence of real numbers, and a real number L is said to be limit of the sequence if for every given epsilon greater than 0, there exists a positive integer k such that Sn minus L, modulus of Sn minus L is less than epsilon. First of all, understand it this way. What do you mean by modulus of Sn minus L less than epsilon? If you just extend this, if you write it, if you split it, we'll get it like this. L minus epsilon less than Sn less than L plus epsilon. Right? What does it mean? You see, You can call a real number L as a limit if there exists a positive integer k such that Sn minus L is less than epsilon for some epsilon greater than 0. What does it mean? You see, you have a sequence of numbers like this, S1, S2, S3. You have so many numbers. When n approaches to infinity, somewhere you will get some kth term. Let us say some sk. You will get some kth term, and all the numbers, whatever you get after this sk, if all these numbers are in between, this interval, L minus epsilon comma L plus epsilon, right? If you get some kth term like sk, after this kth term, whatever the numbers you get in this sequence, if all the numbers lie within this interval, then we say that sequence has a limit, and that is L. Understand what it is? You will get some kth term in the sequence. After this kth term, you will still get so many numbers. If all those numbers, not one or two, if every number after this kth term, if all those numbers lie in between L minus epsilon and L plus epsilon, then we say the sequence has a limit. Then we say the sequence has a limit, and that limit L, that limit is exactly L. And see, symbolically we write like this: limit n tends to infinity, Sn is equals to L. The same way of writing limit in the case of functions. But in the case of functions, that was what you call a continuous function. There it was. I mean, the domain was a set of real numbers directly, but here the domain is set of natural numbers. Remember, a clear difference is there. So there, all the functions, I mean, they were all continuous in nature, but here the domain of sequence is discrete in nature. Okay, that's one case. And when approaches to infinity, if all the numbers of the sequence are with around this number L, if all the numbers in the sequence, when n approaches to infinity, if all the numbers in the sequence are around this number L, we'll take a small neighborhood of L actually. Within that neighborhood, if you find all these numbers, then we say that sequence has a limit, and it is L. And of course, we just pronounce it like this: Sn tends to L as n tends to infinity. And remember, as you know already, in the case of functions, when such a limit exists, it is always unique. I mean, when n approaches to infinity, the sequence cannot go in two different directions. Either it may go towards a finite fixed value, or it may go towards what you call plus infinity or minus infinity. But when all the numbers are going to a particular value, that particular value must be unique only. So when the limit exists, that limit is always unique, right? So this is the basic idea of a limit. Now let me just show you a geometrical idea of this. Now look at this. See, we were speaking about sequences, right? We are writing them as Sn, right? Similar to Sn, here we are writing it as AK. There it was N, and here it is K. The remaining story is quite same. So similar to this, you see, we have actually, we can just assume it is 1 by 2 plus 1 by n. That is the nth term of the sequence. So here, instead of n, they have considered it as K. Understand the basic idea here. When you have a sequence, we can write all the terms of the sequence by taking different values for K. As you can see here, there are different dots. Understand, all those dots represent, all these dots represent numbers of the sequence, right? As we defined, sequence is a set of numbers, right? So these dots represents numbers in the sequence. See, there is no connection from one number to the other number, because they're all discrete in nature. Now see here, you can find two horizontal lines, green color horizontal lines here. You see, one is at 0.6 and one is at 0.4. And see here, this middle point, horizontal or orange color line, if you take that as L, and the distance here you see 0.5 to 0.6 or 0.5 to 0.4, 0.1 unit is there, you see, that distance I'm taking it as epsilon, right? Now see what happened here, how we defined it earlier. You will find some kth term, and after that kth term, whatever the numbers you get, all those numbers lie in between L minus epsilon and L plus epsilon. Exactly here you see, look at this vertical line, just next to 10. Up to 10, you see, you will get all the numbers in blue color, and next to them, there are some other color. So this K, 10th or some 11th number here. This is the kth number here. And after this, whatever the numbers you are getting in the sequence, they are all in between, L minus epsilon or L plus epsilon here. They are all in between these two horizontal lines. Since after this kth term, every number in the sequence is in between L minus epsilon, L plus epsilon, we'll say this sequence has a limit. And to where you have drawn this, where you have taken this interval L minus epsilon, L plus epsilon, it is at 0.5. You see, that's how this sequence has a limit, which is 0.5. Right? Understand, in the definition of a limit, we have discussed about some epsilon also. One may question, sir, what if I take epsilon as very huge? No, you can take it as small as possible, no problem. Even if you take it as very small, see here, this is epsilon. I'm just trying to minimize the value of epsilon. I'm just moving it down. When I move it down, you can see the distance between these two will be reduced. You can observe. Oh, wait a second, I cannot use this. Okay. Oh, something happened. Right, follow this. I'm just moving epsilon down. When I'm changing epsilon, you see the distance between these two horizontal lines is reducing. Right, they are coming closer to each other. Look at this simultaneously. Observe when these two horizontal lines are coming closer to each other. I mean, when the distance epsilon is reducing, corresponding to this epsilon, you will find a different kth number here. You see, earlier it was near to 10 actually, but now it is after 20 here. Corresponding to the size, whatever you are considering here, epsilon, corresponding to that, you will get a different kth number. See, ఇక్కడ మనం ఇంత ముందు చూడండి, ఎప్సిలాన్ కొంచెం తీసుకున్నప్పుడు అరౌండ్ 10 వచ్చింది. ఆ 10th నెంబర్ తర్వాత లేదంటే 11th నెంబర్ తర్వాత ఉన్నటువంటి నెంబర్స్ అన్ని కూడా ఈ ఇంటర్వెల్లో ఉన్నాయి. ఎల్ మైనస్ ఎప్సిలాన్, ఎల్ ప్లస్ ఎప్సిలాన్ ఇంటర్వెల్లో ఉన్నాయి. సో ఎప్పుడైతే నేను ఎప్సిలాన్ వాల్యూని బాగా తగ్గించానో, ఇక్కడ ఎప్సిలాన్ వాల్యూని తగ్గించేసాం మనం. సో దట్ చూడండి, ఇంతకుముందు 11th 12th ఉన్నటువంటి kth నెంబర్ కాస్త, kth టర్మ్ కాస్త ఇప్పుడు నియర్ అబౌట్ 25 దాకా వచ్చింది. సో ఆల్ ద నెంబర్స్ ఆఫ్టర్ దిస్ 25th టర్మ్ are now within the interval L minus epsilon comma L plus epsilon. Right? If I still reduce this epsilon, you can see this vertical line is moving towards, now it is nearly at 40. Now when I take this small value for epsilon, now see, after 40th term, whatever the numbers you will get in the sequence, they are all in and around what you call L minus epsilon comma, within what you call L minus epsilon and L plus epsilon. Now see here, I have taken only up to 50th term in the sequence, right? But now let me just extend it to some 100. I'm just moving this n value towards up so that you can see you will get more number of terms in the sequence, right? I've taken it up to 100. Now see, even if I take up to 100, all the numbers after this 40th term, they're all within this particular interval only, L minus epsilon, L plus epsilon. So if I extend this up to infinity, see, still you can find all the numbers within this interval only. That's how we'll say this sequence has a limit, and that limit is exactly 0.5. Right? I hope you understood this now. To say limit exists to a particular sequence, we'll just find some kth number. After that kth number, if all the numbers in the sequence are within a limit, within the neighborhood of L, within an interval L minus epsilon or L plus epsilon, then we'll say that sequence has a limit, and within what limit you are, within what interval you are getting this, within what neighborhood you are getting all the sequence numbers, we call that number as what you call limit only. Now let me just show you the other graph here. This is 1/2 plus 1/k. Next to this, you see, if I show you this, look at all these things. I'm just taking this epsilon as normal. Now see here, before some 20, let us say some 18 or 19 here. After 18th term, whatever the numbers you are getting in the sequence, they are all, within the neighborhood here. You see, they are all in between these green colored lines, green color dotted lines. If I still reduce this epsilon value, you see, you will still find some other kth number. After 40th term now, all the numbers in the sequence are in between L minus epsilon and L plus epsilon, right? Even if you take more values for n, if you take more numbers, you see, you're still getting all these things. Now see, when I take n approaches to infinity, all the numbers here, they are all just around this horizontal, orange color line. So even if I move up to 200th term here, you see, all the numbers are in between these two. If I still reduce the epsilon here, you can see, you will get some other number. You see, some after 100th term here, every number is in between this. Okay. So like this, after some kth term, if you get all the numbers in the sequence are in between some L minus epsilon or L plus epsilon, we'll say that sequence has a limit, and in whatever the neighborhood you will find all these numbers, we call that neighborhood, that number, real number, as limit of the sequence. In a similar way, if you look at this example, this is blocked again. Look at this, 1 by 2 plus 1 by 2 into sine k. Now see, if you take this epsilon here, you cannot find a particular kth term after which all the numbers are in between these two values, right? The numbers whichever you get after that kth term, they're all not now in within these two values. Even if you just increase the value of epsilon here, you may take any large epsilon, but still you cannot find all the numbers in between L minus epsilon, L plus epsilon here, right? That's how you see, when you cannot find all the numbers within a particular interval, right? Like L minus epsilon or L plus epsilon. Remember that epsilon must be very small value. You see, you cannot take it as some 100 or 200. It will be around 0.01 or 0.001 only. Okay. So when you cannot find all the numbers in the sequence within a particular neighborhood, then we say this sequence is simply divergent, right? This sequence is simply, we call it as a divergent sequence. That's how you can actually define limit of a sequence, right? And as we had seen, when the limit exists, it is a unique value. Now see, depending on this limit, we are going to define about convergence. Understand, when the sequence has a limit, what you had seen just before, you see, when the sequence has a limit, when n approaches to infinity, all the numbers are approaching towards a particular value. And in fact, that is what limit. And if you can find such a limit to the given sequence, we say the sequence is convergent. And we'll also say the sequence converges to limit L, right? When n approaches to infinity, if all the numbers in the sequence are going towards a fixed value, a unique number, we call that unique number as the limit, of course, and we'll say the sequence is convergent to that number L, right? So in simple, you can understand now, when the limit exists for a sequence, then we say that sequence is convergent, right? When the limit exists to a sequence, we'll say the sequence is convergent. And if there is no limit to a sequence, we'll say the sequence is divergent. Okay, as you can observe here, when the limit exists, it is a convergent sequence. And if there is no limit to the sequence, we'll say it is a divergent sequence. And see here, when it is a divergent sequence, probably when n approaches to infinity, the limit may go towards either plus infinity or minus infinity, right? But this is not the only case to get divergence. We'll see the other case also, but intuitively you can just remember it this way. When the limit exists, all the sequence values go towards a finite value. And when it is divergence, normally when n approaches to infinity, in many of the cases, we'll get this limit as either plus infinity or minus infinity. And remember, if you look at this example here, the sequence 1, 2, 3, and so on n is, yes, it is a divergent sequence, because when n approaches to infinity, we'll get all the numbers go towards what you call infinity only. Now, keeping that in mind, you see, you can just refer to these examples. If you take this sequence here, 1, 1, 1, every number is a 1 here. What does it mean? Even if you take n is equal to 1 or n is equal to 2, 3, 4, everything, for everything, we'll get the number in this set as simply 1. You can just write it mathematically. I mean, the rule what you followed here is this: minus 1 to the power of 2n. Right? When it is 2n, always, whether n is positive integer or odd integer or even integer, 2n is absolutely an even integer only. So even when you take n is equal to 1, it becomes minus 1 to the power of 2. So it is plus 1. So when you take n is equal to 2, it becomes minus 1 to the power of 4. Again, it is plus 1 only. So that you can understand, for every positive integer n, will get this sequence of numbers as only 1. And thereby you can see, even when an approaches to infinity, we'll still get the value of this as 1 only. That's how we say the sequence converges to what you call plus 1. In fact, we can just write it like this: Sn is equals to minus 1 to the power of 2n. This is the rule all these numbers follow. And moreover, you see, if you just write a unique number from this sequence, it is simply one number only. We just write only distinct numbers in the sequence, in a set normally. So if it is the thing, for every positive integer, we are getting the output as only 1. So geometrically, if you understand that, you may have infinity values in the set of natural numbers, but all these numbers are mapped to only one number in this sequence. That's how we call this sequence as a constant sequence. Right? It may be 1 or it may be 2 or it may be 3, whatever it is, not a problem. But we call it as, since we are getting a constant number for every n, we call it as a constant sequence. And if you look at the second thing here, you see second example, the sequence 1, 1 by 2, and so on, 1 by n. See, when n approaches to infinity, as we know, when the denominator increases, we'll definitely get that value towards 0. I mean, as n approaches to infinity, all the numbers in this sequence approach towards 0. That's how we say this sequence approach to 0. I mean, the sequence has a limit and it is 0. That's how we say the sequence converges to 0. Right? This is because this sequence of numbers 1 by n approaches to 0 as n approaches to infinity. But if you look at this sequence here, look at them carefully. Here it is first of all minus 1, then it is plus 1, then it is again minus 1, then you see again plus 1. Probably the next number is again minus 1, then plus 1. Alternately, you are getting these numbers, right? See, how can you write this mathematically? If you want to just give a definition. This is, of course, a sequence, and we can define them like this: minus 1 to the power of n. Right? Clearly, there is a mapping. You see how it is. When you take n is equals to 1, minus 1 to the power of 1, it is minus 1. When you take n is equal to 2, we'll get it as plus 1. In particular, you see, when you take odd integers, odd numbers for n, we'll get the result as minus 1. And for all even integers, we'll get them as plus 1. That's how you can understand this comes out as only either plus 1 or minus 1 at the end. Right? So, is it now converging? When n approaches to infinity, we are not going towards a fixed number. Right? For odd integers, we are getting minus 1, and for all even integers, we are getting here this as plus 1. Since the sequence of numbers, since all the numbers in the sequence are not going towards one single finite number, we can say this sequence is divergent. I mean, we can say the limit doesn't exist in this case. To say the limit exists, all the numbers must go towards a single number. But here, we are going, the sequence is, the numbers are going to two different numbers. That's how we say the limit does not exist for this sequence, and therefore it is divergent. Earlier, you see what we said. To be a divergent sequence, when n approaches to infinity, we took this as, Sn, limit n tends to infinity, Sn as either plus infinity or minus infinity. But you see, this is another case. Right? Even in this case also, we say the sequence is divergent. To be divergent, either the limit may be plus infinity or minus infinity, or the limit may not exist at all. But see here in these cases, when you get 2 or 3 values like this, when n approaches to infinity, function values, the sequence of numbers are going to two different numbers. In that case, you see, we call those sequences as oscillating sequences. Understand this definition? If the sequence of real numbers Sn diverges, yes, it is diverging, but it is not diverging to either plus infinity or minus infinity. In that case, we call that sequence as what you call an oscillatory sequence or oscillating sequence, right? See, if you take, this example particularly, you can understand it this way. If I define one example here, like minus 1 to the power of n into n, if you take this, see, now in this case, if you take n is equals to 1, we'll get it as minus 1. If you take n is equal to 2, we'll get minus 1 to the power of 2, you see, plus 1 into 2, it is 2. Then when you take n is equal to 3, it is minus 3. Then we'll get 4, then minus 5, then 6. You'll get all the numbers. If you just write them in a proper order, we have starting numbers as these two, minus 1 and 2. And here we'll get them as minus 3, minus 5. It goes towards minus infinity in this direction, right? On the other side, if you see 2, then 4, 6, you'll get all the numbers, and all these are going towards plus infinity, right? So now this sequence has numbers which are going in both the directions. I mean, it is going to both plus infinity as well as minus infinity, right? Then also we say this sequence is what you call divergent. I cannot say this is oscillatory. To be oscillatory, remember, we must have two finite numbers, 2 or 3 finite numbers, not a problem. When n approaches to infinity, if all the sequence of numbers are approaching to 2 or 3 different finite numbers, then we say that as a finite, what you call oscillatory sequence. But in this case, on both sides, the function is, I mean, the sequence is diverging. It is going towards both plus infinity as well as minus infinity. So it is simply a divergent sequence, right? So like this, we can define what a sequence, then we can also define what you call limit, then we can see convergence of a sequence. Now see, next to this, we need to define actually what you call a bounded sequence. And next to that, you see, when you are given a sequence, we need to identify whether that sequence is convergent or not. So how you are saying convergence? When the limit exists, when n approaches to infinity, if the limit exists, then we say the sequence is convergent. So for different sequences, we need to see whether they are convergent or not. I mean, whether such a limit exists or not, we need to see. So we'll discuss those things in the next class.